Welcome back, students, to the second part of our discussions from the lesson Work, Energy and Power. Today, we will proceed further in the lesson. In the previous class, I had told you what is the physical interpretation of work done. We had studied that work is said to be done by a force acting on a body provided the body is displaced actually in any direction except in a direction perpendicular to the direction of force. We had completed our discussions up till conservative and non-conservative forces. We had seen that in a conservative field work is independent of path, while when the work done is that due to of a non-conservative force, then the work done by or against the force in moving a body from one position to another depends on the path followed between these two positions. Today we will cover up the topics that is coming on your screen right now. We will discuss what is power, what is energy, what are the different forms of energy, how can we bring about a transformation of energy, and we will be discussing about kinetic energy and the work energy theorem. Let's begin today's discussion with the topic power. Power of a body is defined as the rate at which the body can do the work. That is, power is equal to rate of doing work, which is further equal to work by time. As you can see in the formula, P is equal to W by T. W stands for work done and T stands for the time taken. Power of an agent measures how fast it can do the work. When a body takes lesser time to do a particular amount of work, its power is said to be greater. The power of an agent can also be expressed in terms of the force applied and the velocity of the body. As we know that power is equal to work by time, which is further equal to force dot displacement. The formula for work is force dot displacement and divided by time. Now, as you can see, we can modify the expression as power equal to force dot displacement by time. We know the displacement by time is velocity. So the formula for power turns out to be power equal to force dot velocity. Hence, power of an agent can be expressed as the dot product of force applied and velocity of the body. Now, is it okay to write down power as a vector? Obviously not, because it is the dot product. So power is purely a scalar quantity. So we can write down P is equal to F dot V. Dot product of two vector quantities is a pure scalar. Now if theta is the angle between F vector and V vector, then F dot V can be written as F V cos of theta. So obviously, when the velocity of the object is along the direction of the applied force, theta will be equal to 0 and P can be written as Fv cos 0 degree, that is force into velocity. What are the dimensions of power? The dimension of power is m L to the power 2 and T to the power minus 3. The absolute unit of power in SI is watt. As you can see right now on the screen, 1 watt is equal to 1 joule per second. Hence, power of an agent is said to be 1 watt if it can do 1 joule of work in 1 second. There are several bigger units of power like 1 kilowatt, which is equal to 1000 watt, 1 megawatt, which is equal to 10 lakh watts. Another popular unit of power used mostly in engineering is horsepower, which is written as HP. And 1 HP is equal to 746 watt. If we plot a graph for work versus time, then it will come out like this. So the slope of this work versus time graph, for that we have to consider the tangent. So the slope of work versus time graph gives us the instantaneous power. As you can see in the picture. Similarly, if we draw a graph of power versus time, then it comes somewhat like this. So from the graph, if we calculate the area, then area under power versus time graph gives us the work done. So W is equal to integral P dt, and that is equal to the area under the power versus time curve. Let us now discuss what is energy. Energy of a body is defined as the capacity or ability of the body to do the work. When a body is capable of doing more work, it is said to possess more energy. The reverse is also true. Like work, energy is a scalar quantity, having magnitude only and no direction. The dimensions of energy are the same as the dimensions of work, which is m L to the power of 2 and t to the power of minus 2. The units of measurement of energy are also the same as the units of work. That is, in SI, the absolute unit of energy is joule, and in CGS system, it is erg. Energies of several types. For example, mechanical energy, heat energy, sound energy, light energy, magnetic energy, electric energy, atomic energy, nuclear energy, chemical energy, solar energy, and so on. It is possible to bring about a transformation of one form of energy into another. Like as you can see in the picture right now, like we consider one example, chemical energy transformed to motion and then transferred to electrical energy. We can consider the example of several energy converters. Like for example, let us consider the example of an electric generator which converts mechanical energy to electric energy, a DC motor which converts chemical energy obtained from the source of current, which might be a battery. So it is utilizing that chemical energy, and that chemical energy is getting converted to electrical energy, and that electrical energy is utilized in bringing about motion in the coil. So obviously the final form of energy is mechanical energy. So in this way, one form of energy can be converted into another with the help of several energy converters, and this is actually known as transformation of energy. At this level, we shall confine ourselves to the study of mechanical energy, which is primarily of two types, kinetic energy and potential energy. But today we will be discussing only about kinetic energy. Kinetic energy. The kinetic energy of a body is the energy possessed by the body by virtue of its motion. As you can see, couple of examples has been shown in the picture alongside. For example, a bullet fired from a gun can pierce through a target on account of kinetic energy of the bullet. Windmills work on the kinetic energy of air, water mills work on the kinetic energy of water. A nail is driven into a wooden block on account of kinetic energy of the hammer striking the nail. You can see several such examples shown in the picture. Let us obtain a formula for kinetic energy. Kinetic energy of a body can be obtained either from the amount of work done in stopping the moving body or from the amount of work done in giving the present velocity to the body from the state of rest. Let us use the second method. Suppose m is the mass of the body at rest. So in this case, m is the mass of the body and initial velocity is equal to 0. As you can see in the diagram, F is the force applied on the body. A shall be the acceleration produced in the body in the direction of force applied. V is the velocity acquired by the body in moving through a distance s. From the third equation of uniformly accelerated motion, we get V square minus U square equal to 2as. Substituting u equal to 0, we get v square minus 0 equal to 2as. That implies a to be equal to v square by 2 into s. Now we know that F is equal to m into a from Newton's second law. So let us substitute the expression for acceleration in this formula. So we get F to be equal to m v square by 2 into s. Therefore, work done, that is equal to force into distance, will be equal to m v square by 2s into s. So you can cancel out s and you get work done to be equal to half m v square. This work done on the body is a measure of the kinetic energy. Therefore, kinetic energy of the body is equal to the work done, that is equal to half mv square. This is one way of finding out an expression for kinetic energy. Let us try an alternative method. The formula for kinetic energy of a body is also obtained by the method of calculus. For this, again, let us assume an object of mass m, which is initially at rest. If the applied force is denoted by F, for a very small displacement ds produced in the body in the direction of the force applied, small amount of work done by the force dw, that will be equal to, for a very small displacement ds, work done, small amount of work done will be F dot ds, that is equal to F ds cos of 0 degree, and that is equal to f ds. If acceleration a is produced by the force, then we can write down f to be equal to m into a, which is further equal to m dv by dt. So now we get dw to be equal to m dv by dt into ds. We are substituting in this expression. So now we get this to be equal to m ds by dt into dv. ds by dt is v, so we get dw equal to mv dv. So obviously for total amount of work done, we have to integrate both the sides. So integrating both sides over the limits, when the object was not moving, work done was 0. When the object acquires a velocity v, total work done is w. So over the limits, we integrate both the sides. As the mass is constant, so we can take it out of the integral sign. So we get equal to so this will be equal to m v square by 2 over the limit 0 to v. Therefore work done comes out to be equal to half mv square, and this work done is an estimate of the kinetic energy. So kinetic energy is equal to half mv square. Thus kinetic energy of a body is half the product of mass of the body and square of velocity of the body. We observe that kinetic energy is directly proportional to m, and also kinetic energy is directly proportional to v square. That is, a heavier body and a body moving faster possess greater kinetic energy. The reverse is also true. The absolute unit of kinetic energy on SI is joule, and on CGS system it is erg. Kinetic energy of a body is always positive. It can never be negative. Kinetic energy of a body depends upon the frame of reference. For example, kinetic energy of a person of mass m sitting in a train moving with velocity v is half mv square in the frame of earth, and kinetic energy of the same person is equal to 0 in the frame of the train. Let us now study a relation between kinetic energy and linear momentum. If m is the mass of the body and v is the velocity of the body, then linear momentum p is equal to m into v, while kinetic energy is equal to half mv square. Now let us do a bit of substitution. From here we can write down v to be equal to p by m. On substituting in the expression for kinetic energy, we obtain half m, and for v we can write down p by m, and then that is squared. We obtain this expression. We can cancel out one term for mass, so that gives out the relation between kinetic energy and linear momentum as equal to p square by 2m. This is an important relation. It shows that a body cannot have kinetic energy without having linear momentum and vice versa. Now, if momentum, linear momentum is constant, then obviously kinetic energy will be inversely proportional to m. This is shown in this graph. If kinetic energy is constant, then p square is directly proportional to m, or p is directly proportional to root over m, as you can see in the second graph. And if m is constant, then p square is directly proportional to kinetic energy, or we can write p is directly proportional to root over kinetic energy. So we can obtain a graph like this. Let us now study a very important topic, that is work energy theorem. According to this principle, work done by a force in displacing a body measures the change in kinetic energy of the body. Thus, when a force does some work on a body, the kinetic energy of the body increases by the same amount. Conversely, when an opposing or retarding force is applied on a body, its kinetic energy decreases. The decrease in kinetic energy of the body is equal to the work done by the body against the retarding force. Thus, according to work energy principle, work and kinetic energy are equivalent quantities. To prove the work energy principle, suppose m is the mass of the body, u the initial velocity of the body, f is the force applied on the body in the direction of motion, ds is the small displacement of the body in the direction of force. Then obviously small amount of work done by the force is equal to f dot ds, which is equal to f ds cos of 0 degree. So dw should be equal to f ds. Now we know that force is equal to mass into acceleration. Therefore dw will be equal to m a d s. For acceleration, we can write down dv by dt. So the previous expression can be written like this. Further, we can write down dw to be equal to m ds by dt into dv. ds by dt is velocity, so we can write down dw to be equal to mv dv. So now total work done by the force in increasing the velocity of the body from u to v will be equal to integral over the limits u to v mv dv. And that gives us work done to be equal to m, which is a constant quantity, and on integrating we get v square by 2 over the limits u to v. So obviously, going by the rules of definite integration, we get work done to be equal to half m v square minus u square on substituting the limits. So we get work done to be equal to half m v square minus half m u square. Half mv square is the final kinetic energy and half mu square is the initial kinetic energy. So we can write down work done to be equal to change in kinetic energy. Hence, work done by a force is a measure of change in kinetic energy of the body, which proves the work energy principle. Now, in the above discussion, we have assumed that the work done by the force is effective only in changing the kinetic energy of the body. It should, however, be remembered that work done on a body may also be stored in the body in the form of potential energy. When kinetic energy of a body decreases, work done on the body must be negative and vice versa. Conversely, when work is positive, kinetic energy will increase, and when work is negative, kinetic energy will decrease. Work energy principle theorem is true for any system of particles in the presence of all types of forces. These forces may be conservative or non-conservative. When we consider a system of particles and the particles exert force on one another, then change in kinetic energy of the system is equal to work done on the system by the external as well as internal forces.